Hello everyone! In this video we will continue to examine topic 7.1 discrete energy and radioactivity, and in particular we will continue to unpack the concept of half-life. So, in the last video we saw how the fundamental relationship governing radioactive decay led us to an expression for the number of nuclides as a function of time. That is, n of t equals n naught e to the negative lambda t. This is exponential decay, or a case of exponential decay. And what it means is that the number of nuclides is decreasing sort of by the same amount or same percentage, I should say specifically, for every constant amount of time. We usually catch this out in terms of the half-life, which is the time it takes for half the sample of nuclides to decay. So if we have a particular time it takes us to go from n naught to n naught over 2, then it will take us exactly the same amount of time to go from n naught over 2 to n naught over 4, and from n naught over 4 to n naught over 8. This makes a very distinctive sort of decreasing curve in the way that is shown. And that curve is governed by that fundamental equation n of t is equal to n naught e to the negative lambda t. You can see that I have forgotten that, so I'm just going to go insert that constant in there. Alrighty. So given that, well, how is the half-life related to lambda? Okay, so that's an important question. How is the half-life related to lambda? Remember that lambda is the probability of undergoing a particular decay. And so we can sort of, at least conceptually, think that, well, if the probability of undergoing a particular decay in the next second is higher, then we'd expect the half-life to be shorter. So these two quantities should be related, and it's not a terribly outrageous guess to assume that they would be inversely proportional. The higher the probability of undergoing decay, the smaller the time it should take until you're at half the original sample. But we can go ahead and prove that. So the way we're going to do it is we're going to start out with that fundamental equation here, that is n of t equals n naught e to the negative lambda t. And we're going to say, okay, well, if the number of particles, n of t, is exactly equal to n naught over 2, that is the original number of nuclides divided by 2, then that's going to be equal to n naught times e to the negative lambda t sub 1/2, where now t sub 1/2 is a particular time, the half-life, and the number of particles at that time, t sub 1/2, is exactly n naught over 2, by definition. So if we write that down, then we can say, okay, well, this is independent of the number of nuclei. I can cancel out n naught. And so I get 1/2 equals e to the negative lambda t sub 1/2. And that means I can solve for t sub 1/2 here. Okay, so I can take a logarithm of both sides and divide by -1. That gives me negative log of 1/2, otherwise known as log of 2, or ln of 2. So we have the natural logarithm of 2 divided by the decay constant is equal to the half-life. This equation right here, HL physics will use. SL physics, it's just good to know, but it's the relationship between the decay constant shown in our original equation and captured here in the equation for exponential decay, and the half-life. If you know one, you can figure out the other, and vice versa. Now, what SL physics will need to do in analyzing radioactive decay is simply to be comfortable with the idea of using multiple integer number of half-lives to predict a result. So the idea is if I tell you that there are 3 half-lives or 4 half-lives later, you should be able to predict the number of particles we're at that point. Okay? And that just involves sort of multiplying by 1/2 the appropriate number of times. So if we consider the beta minus decay of thallium into lead, then that thallium is turning into lead, or transmuting into lead via beta decay. And the number of our original nuclide can be modeled by exponential decay. for the reasons that we just discussed. Now, without taking measurements, there's no way for us to know that decay constant or the half-life. But if we do take some measurements, we discover that the half-life is approximately 3 minutes. So the half-life, that is the time it takes to go from our original sample to half the original sample, is 3 minutes. Notice that with successive half-lives, you cut it by a quarter, and then an eighth, and so on and so forth, just as described. Notice you may also be required to go the other direction. So if you are told that the number of nuclei at this point is, for example, reading off this chart, 0.2 times 10 to the 22, but you've been told that 3 half-lives have passed, you should be able to multiply by 8 to get the original number of nuclei at 1.6 times 10 to the 22. And those are the only questions you'll be asked. So you won't, at SL, have to or be required to use this fundamental equation, although it's a good idea to understand that this equation is what all of these data points lie on. So this equation fundamentally governs exponential decay. HL physics, you should be comfortable both with the definition of half-life and the fundamental equation governing exponential decay, and we will discuss that more in a later video. Notice here that the second graph is simply showing that the number of lead particles from the thallium beta decay is increasing at exactly the same rate that the number of thallium is decreasing. Why? Because every time one of these red particles undergoes a decay, you get a blue particle. Every time a thallium undergoes decay, you get lead.